In that case, very happy to have everyone here, both in presence and virtually, for Evan's thesis defense. It has been great working with him over the years, and I am very excited for you all to hear what he's been working on. So, take it away. Oh, let's keep, if you have clarifying questions, I'm watching the chat, or turn on the microphone and ask a clarifying question, or in the room. But big questions, let's keep to the end. And for procedure, if you haven't been to one of these before, Evan will talk for about 45 minutes. Then all of us will have the opportunity to ask questions, and then we'll kick everyone except for Evan and the committee out, and then we'll grill him with questions, and then make our assessment. So, secondly, without further ado.
All right, well, thank everyone for coming. Not quite sure where to look. I have some family members here and Sinead, and then everybody else is online. We'll make it work. So thank you for coming today to my defense. Sinead already addressed the clarifying questions, so I will go ahead and get started.
I'll do it.
All right. So today I'm going to go over the 3 main projects I worked on over the course of my dissertation. For each of them, I'll talk a little bit about the background of that particular project, and then talk about the methods that I created and go over some results. For that, though, I'll give a more general overview to all of this line of work in general. So, neural networks are fundamental basis of my work. So neural networks are these highly flexible models. They can capture all kinds of complicated data relationships. That's probably not a surprise to most of the people on the call, but they have applications in everything ranging from medicine to quantitative finance to computer vision, high energy particle physics. I think I saw a headline about Bitcoin or something today. I don't know. While these models are great in practice for a lot of things, typically we learn them with maximum likelihood estimation. So to try to identify the appropriate parameters, we typically use that approach, or minimizing a loss more generally. And if we have tons and tons of data, that's a great approach. It's relatively easy to implement with existing tech software. But one thing that fails to do is it fails to address any model uncertainty that we have. Separately, when we're thinking about using neural networks in problems, typically we're using them in deterministic settings. So that might be a regression setting, but even our approach to classification is more about finding the top 1 or top 5 and not really treating it in a probabilistic way. So all of these projects are inspired by Bayesian methodology in some way, and we're going to be looking to incorporate uncertainty in neural network-based models. So I'll reintroduce each of these as we go, but the 3 projects that I worked on here that I'll be exploring, the first explores methods of approximate Bayesian inference in neural networks. The second takes a slightly different approach, so we'll look at a normalizing flow model, kind of a subclass of neural network models, and we'll look at a Bayesian-inspired posterior distribution. We'll get into the details of both parts of that to get there. And then finally, inspired by some results in Bayesian nonparametrics, we'll look at a graph neural network model that can generate graphs in an interesting and novel way. So let's take a look at the first project. So this first project is going to appear as this paper, Spike Lab Probabilistic Backpropagation, at the I Can't Believe It's Not Better workshop at NERICS this Saturday. That might be giving away or bearing the lead or whatever a little bit. That's fine. All right. So let's talk about this approach. And to do so, let's first be a little bit more concrete about the neural networks we're interested in. So we'll consider feed-forward neural network, multi-layer perceptron, we'll gather all of the weights and biases together with the script W. The basic idea in these simpler neural network models, we'll take some input X and take a linear transformation and then apply some nonlinearity, usually element-wise, and construct many layers to have some final output. The maximum likelihood setting, that might be our final prediction. If we want to incorporate a Bayesian method here, we'll have a explicit likelihood. So the particular problem that we're going to look at, we're going to be mainly focused on regression. So we'll take the final output, that's Z with a sub capital L, and assume that our data is distributed as a normal distribution where that's the mean with some noise parameter. To construct the fully Bayesian model, we'll include a prior typically on the weights, which is typically going to be Gaussian. We'll revisit that choice of prior in the next project, actually. But even for a relatively straightforward description of this model, perhaps unsurprisingly, the posterior is going to be intractable in closed form, which begs the question, what are we going to do? So a lot of existing work on this kind of problem. And so some of the existing approaches, we could look toward MCMC, but those methods are slow. And if we think about models where we have many tens of thousands or millions of parameters, pretty unrealistic to use in practice. We could turn to things like the Laplace approximation, but that's quite sensitive to the local geometry about the maximum a posteriori. One common approach is variational inference. It's not the subject of the work today, but it's one of the more common approaches here. And while it's becoming quite supported in software to be able to do that kind of black box approaches, this does require sampling from an approximate posterior in order to propagate anything through the network. So it's certainly fine, but maybe we want to do something closer to closed form solution. So this other line of work, and there's a few ways of doing it, is going to explore constructing a parametric form of an approximate posterior. I'm going to call that Q of the script W. And an approximating distribution on the messages is what I'll call them for the output of each layer. So if we were to assume this form of approximate posterior and propagate the probability distributions through the network, what would that resultant distribution look like? And we'll try to do that in closed form. We'll have to make some approximations along the way, but that's a general approach. So in this work today, we're going to be following probabilistic backpropagation. Miguel knows a lot about that. So in this approach, we're going to assume a mean field Gaussian approximate posterior on the weights. And more critical to our work that I'm going to talk about here is we're going to approximate these message distributions in both linear layers and the ReLU layers as Gaussians using moment matching. So let's take a look at what that looks like. So if we were to think about just the first layer of this feed-forward neural network, we have our inputs, which we might assume are known with complete specificity, zero variance. We have our approximate posterior on the weights and biases that are all Gaussians. We know what that distribution should look like. This is the correct distribution there, where we have a mixture distribution of a spike at exactly 0 mixed with a truncated normal that's truncated to the positive part of the real line. So that's what you see on the figure on the left there for a particular sample distribution here, where I've also overlaid the probability mass as that thick black bar and a probability density, just for ease of representing it here. So in the existing approach, we're going to kind of squint at that, call that a Gaussian, and there's some good reasons for doing that. But you know, one of the reasons that we might enjoy using the ReLU in a typical neural network setting is that it's trying to represent this sparsity in the network. If we think about a node as extracting some kind of feature, having an output of 0 is really saying that that feature is turned off. And we'll lose that if we just approximate everything with Gaussians. So the question was, can we do something better? So we're going to propose using a spike and slab approximation for these message distributions, where we're going to have a mixture of a spike at exactly 0, but due to the computational complexity of using truncated normal distributions, we'll just have a Gaussian as the other mixture component. Yeah, a little bit of water. In particular, we'll use a non-central slab. So we'll have a mean and variance parameter as well as a parameter for how much of the probability mass is on each component there. Now, if you're interested in the dissertation, you can go through the appendix. Did a lot of math to show that for any given distribution P, the approximating distribution Q that would minimize the KL of P and Q is actually something extremely intuitive. So what it works out to is we moment match the total mean of our target distribution against the total mean of the spike and slab. We match the variance, and we match the mass that's on the spike. Highly intuitive, but that's what we ended up with. So as a result, we can also then compute drop-in replacements for what PBP uses for linear layers and for ReLU layers, and now start using that instead. So we would expect that because we can explicitly model that sparsity, we'd be able to model the distribution better and might be able to see some increased performance. Okay. So here's that same figure, but now with RFIT on the far right, where we'll match the spike probability exactly. And we won't quite capture the form of the truncated normal, but this would be the particular fit here. So a mix of the spike and the non-central slab. Okay. As a first study of why we think this might work, here's a little synthetic example for arbitrarily chosen normal distributions on a random variable X and W, treated as independent, that we then pass through a ReLU. And here we're looking at the MMD between ground truth samples and samples from these, if we apply our approximation and then take samples from it. And our version, certainly for combinations where there's a lot of mass that should be on the spike, perhaps unsurprisingly, our MMD is a lot better. It's smaller, so we're more able to capture the true distribution there. Perhaps it's unsurprising, but kind of a cool result. And we do see that in cases where all of the samples are very far away from 0 and very positive, maybe we don't do quite as well. But certainly when there's significant sparsity to represent, we seem to win. That's cool. So let's apply that to some real data sets. So we explored several different configurations of model architectures here. The results are similar throughout all of them. I've chosen one particular architecture here. And what we see is we kind of win about half the time, but if you go and look at all of those confidence intervals that would result, everything pretty much overlaps. There's no clear winner. That was kind of confusing. We wondered why, if we introduced this much smarter approximation, why are we not seeing benefit? So a lot of math later. And first of all, we figured out intuitive result that if we have a bias, which is very typical in the neural network setting, that's going to force the true distribution spike probability to be 0. So there is no sparsity in that case after a linear layer. Okay, that's kind of a bummer. But maybe we, because we've modeled sparsity along the way, maybe we still get a better result. Well, as it turns out, we can formally prove that PBP and spike and slab variant will give exactly the same approximation after a Rayleigh layer and then a linear layer for the same approximate posterior. So we'll end up with an identical solution. So we've made exactly 0 improvement. Okay. But to further explore this a little bit, what happens if we construct an atypical neural network where we remove the bias? So we would have the ability of having sparsity being carried through the network. What happens in that case? So these are results on a bias-free version of both. Overall, the models perform a little bit worse than their more typical counterparts. And in some cases here, we seem to maybe win, but again, this really seems to be more due to chance than anything else. If you're looking through multiple different architectures. So we still don't really see an improvement. So in work that this led us to the suspicion, which we've then actually played with a little bit in some preliminary work, that it turns out we just don't end up with much mass on the spike in a lot of different architectures, which kind of makes sense. You have to have every single element in the previous layer have significant mass on the spike and then do the linear transformation. Kind of makes sense that having to have all of those be 0 for the results to be 0. So what we learned here, turns out Gaussians are really effective. We already knew that, but turns out they're extremely effective even in this case. Our results on the bias-free version make us suspicious that a possible next step could be introducing a spike and sub approximate posterior on the weights rather than on the messages. But because for especially wide layers, we'd end up probably with very little mass on the spike, maybe it wouldn't make much difference anyway. In future work, we could explore other approximations. For the message distribution, we could consider maybe near 0 values. We could collapse them onto the spike, something like that. But this was an interesting project because we did something that should have been smarter, but it failed, and it failed in a kind of interesting way. So we'll be talking about that at NeurIPS on Saturday. Okay. So in this project, we looked at a Bayesian approach to neural networks. Now we're going to turn to an alternative approach to posterior inference in the normalizing flows setting. I guess I could check if there's any clarifying questions before we move on to the next project. All right, so here we're going to look at another line of work. This is on non-parametric posterior normalizing flows. This is work that is also, some of what's represented here is currently under review for AI stats spring. Okay, so normalizing flows may not be as familiar of a technique, but in the normalizing flow setting, we're going to try to model a potentially complex distribution with a usually simpler latent distribution H, and then we'll apply some transformation G phi that we will call a flow and perform a change of variables. So for example, the latent distribution that we might have could be a standard normal. It's fairly typical. And using clever choices of the flow architecture, we can model extremely complex high-dimensional distributions. We can even include neural networks as part of that transformation if we're careful in how we construct it. This lets us do some really impressive work on density estimation, for example, that we can do in closed form, and a lot of work goes into constructing methods where the Jacobian is simple to do in closed form. Okay. Similar to neural networks generally, Normalizing flows are typically trained with maximum likelihood. So again, we're going to ignore model uncertainty in the typical setting. If we want to be Bayesian, again, we're going to have an intractable posterior, just as we saw before. But one of the things that this approach made us question is, in the Bayesian neural network setting, and in this setting, if we were to include a kind of typical standard normal prior on all the flow parameters, it's not really clear what that represents and how that genuinely expresses subjective uncertainty in the model parameters. And it's somewhat dubious that that does represent it. And even so, it's just not intuitive as a prior. So we wanted to ask the question of, can we incorporate model uncertainty in some way, but maybe also include a more intuitive representation of our prior beliefs? So for that, we're going to turn to look at some work on non-parametric learning. So we'll take a step back just for a moment, kind of get the big picture here, and consider if we have some random variable of interest that is distributed according to the true data generating distribution F naught. And let's assume we have some parameter of interest theta naught. Now, as a thought experiment, if we had infinite data, or if we had direct access to the true data generating distribution, how would we approach estimating our parameter of interest? Well, we'd probably use maximum likelihood. If there's no model uncertainty, it's very reasonable to do so. So in that case, we would get a result like this for theta naught based on our true data generating distribution. So to reframe the problem of inference just slightly, we can think about, if we have only n observations, x1 through n, how are we going to represent uncertainty about the remaining observations? Or equivalently, how do we represent uncertainty about the data generating distribution F naught? So non-parametric learning is an interesting and recent approach that's very inspired by Bayesian inference, but takes this different tack where we're going to think about expressing our uncertainty about F naught using a distribution, be able to construct a posterior distribution about our beliefs about the true data generating distribution. And with that, then we can construct what we'll call a non-parametric posterior on theta, given some data. So that's given here. We'll talk about a specific form in just a moment. But assuming that we have access to that posterior in some way, including by a Monte Carlo estimate, we can sample from the non-parametric posterior. Janae, go ahead.
Oh, I'm sorry.
No worries. Still no James. That's
No, we got James.
Oh, we did.
Yeah,
Oh, hi,
we got
James.
James just as you started.
Oh, cool. Hi, James. All right. So, following the approach of Feng et al., one of the approaches to non-parametric learning, we'll take a relatively simple prior here where we'll assume that our data generating distribution is the realization from a Dirichlet process with some concentration parameter alpha, some centering distribution at pi. We'll come back to f pi in just a moment. If we have that, given some observations x1 through n, we have a well-defined posterior distribution on f naught. We can then use that to get bootstrap samples of the non-parametric posterior on theta. So thinking about our possible choices for f pi, it's really pretty general, but in particular, an interesting one is if we have some historical data, we can represent that as an empirical distribution and have this prior in the space of the observations that we then use directly to incorporate prior information, prior uncertainty. So it's a pretty cool technique. Okay. So this is a quick overview of what that looks like in practice if we were trying to obtain samples of our non-parametric posterior on theta. We can sample, obtain a realization from the posterior on the data generating distribution. And then, essentially for the cost of a maximum likelihood estimation, we can obtain a sample of theta. And there's a finite approximation to this as well. A particular note to connect with some other lines of research, if we take the degenerate prior here, so if alpha is 0, then this technique actually corresponds to the weighted likelihood bootstrap and the Bayesian bootstrap as well. So this is great. This is a really interesting way of incorporating uncertainty in our inference, but if that minimization for each theta is expensive, this is not going to be computationally tractable if we want many samples of theta. So in particular, for a normalizing flow model that we might expect to be deep with lots of parameters, this is going to be expensive. What can we do? So whereas the naive approach in this setting would be to learn B independent normalizing flows, which we might be able to do in parallel, but probably would still be expensive. We're going to propose a slight reparameterization of normalizing flows where the latent distribution will have a parameter that we'll learn, so we'll call that theta, but all the flow parameters will be shared, so it's that phi. So in this setting, we'll learn phi globally by gradient descent, but as it turns out for this particular choice where our latent distribution is a normal with a unknown mean, that mean is actually available in an analytical, tractable way by just weighting the mean of the pre-image of X. So we can get samples, bootstrap samples of theta from our non-parametric posterior for cheap once we train the flow. We propose a method to do that. If you're curious, we can talk about that maybe in the Q&A time in a little more detail, but we'll learn a particular realization of phi, and then we'll have this latent distribution where we'll have a theta for each bootstrap sample. Okay. So for a particular flow model, this is the masked autoregressive flow. Hopefully y'all can hear me over the rolling things nearby. In the top left is, we're looking at a Gaussian mixture model, synthetic example here to get a feel for how this behaves. So in the top left is a flow trained by maximum likelihood where we take samples from the resultant flow. The bottom left is the degenerate case where alpha is 0. So in this case, we're not really incorporating prior information, but the difference would be that we're in some sense adding some stability to the model. We're doing a more robust version of learning here. And in both cases, we end up with roughly the same kind of behavior in this synthetic example. If we look on the far right, when we've increased the concentration parameter to 100, which is the same size as the data set, so we're kind of equally weighting our observations that are shown in black with the prior that's labeled above, we see that we're able to influence the flow with the prior distribution that we placed on F naught. So in the top, we have a prior that's tightly concentrated around 0, 0. Bottom right, we have a prior that's more diffuse, and you see that we can reflect that in our resultant models and the samples from those models. Okay. Let's take a look at some empirical results. So these are 5 different data sets where in black, we see the results from a maximum likelihood trained model. And on the vertical axis, we're looking at the test set log likelihood. On the horizontal axis, we're looking as we increase the size of the training set. So as we go from left to right, we would expect the model to improve. We give the model more data, should be able to have better test set log likelihood. And what we're exploring here is then three different versions of our method. So one is the degenerate prior case. So essentially letting the model be a little bit more robust. Although it does seem to have some stability issues. So in blue, you'll see those error bars, kind of large. Versus two versions with a relatively high concentration on our prior. So in orange, we have kind of the best case scenario where our prior for the prior centering measure f pi is given as an empirical distribution of additional training data. So might call that cheating, but representing a best case scenario, what happens? And in that case, well, let me talk about the other one first. So in red, we have a simpler prior where we've computed the mean and variance of the training set, applied a f pi where we have a Gaussian with that mean and variance. So we're not really giving additional information to the model. Maybe a little bit of structure, calling it a Gaussian. These data sets are kind of vaguely Gaussian. But even that one at small n is able to provide much better performance. So we're not really even giving the model much more to go on, but we can have improved performance. Certainly, if we have additional training data, we're able to do well. And as we increase in, as expected, the maximum likelihood sometimes outperforms ours, but that's relatively expected. If we have enough data for relatively simple data sets, maximum likelihood is going to win just because we don't need to incorporate model uncertainty as strongly. Okay. But take home is for small n especially, this provides a really interesting way of incorporating model uncertainty where we can see increased performance with borrowing from, say, historical data. As a brief test, we also looked briefly at what happens if we were to implement the naive method. So if we have independently trained flows and then take samples from each of the independently trained flows. That one seems to actually perform the worst compared to our method or the maximum likelihood method. Suspect that that's just because flows are a little bit unstable to learn. So our model or the maximum likelihood model will just inevitably be a little bit more stable. We do find that our method, even with the degenerate prior, ends up with a better average test set log likelihood. It's nice. So this was a really cool project. There's a lot of future work that we could do here where we look at different choice of flow architecture that's explored as joint work in the paper a little bit. And here we focused on a relatively simple case of prior centering measure and a extremely best case scenario, more data from the same data generating distribution. But I think there's a lot of interesting applications here where you could use historical data, where you could think about a related data set and some kind of transfer learning type of approach. But I think this is a really cool approach that for the cost of a maximum likelihood, more or less, we can really incorporate model uncertainty and a prior. Okay. I'll take a beat there. So if there's any clarifying questions on that project.
I think given we're running a little late.
Okay. All right. So third project, edge-based generative graph neural networks. So this is a part of a larger collaboration. Elahe Galevi has done some work on link prediction, so kind of parallel work to this one. But we'll jump right in. So graph neural networks are a way of letting us be able to make better predictions about data when we have some kind of relational data that goes alongside of it. So we're able to leverage relational structure to make better predictions. Typically, what we're trying to do is we're trying to take instead of just the covariates that we have, we're going to leverage relational data and construct node embeddings. So I'm going to denote that as HV for each node in the graph. And typically this is done with a message passing scheme. So for example, in this graph to the right, node number 1 will receive messages from nodes 0, 4, and 9, its neighborhood, and then aggregate those messages in some way, and then update its embedding based on those messages. And we'll typically have a neural network based model for the messages that might include any covariates we had for the sender and the recipient. If we have any edge related information along with the sender's node embedding, we'll aggregate those in some way. In this case, I'm just taking the sum, other options are available. And then we'll have another neural network, which I'll denote here, F update, that takes in those messages and the existing embedding, produces a new embedding, HV prime. There you could consider a recurrent neural network, for example, and that's what we'll use in our project. So graph neural networks are really interesting models. They're great for node classification, so trying to predict the class of each node. They're interesting for graph classification as well. Say if each graph represents a molecule in a drug discovery kind of paradigm, we could do things there. But one line of work takes this and applies it to a generative setting where we're trying to explicitly construct a distribution on graphs. So rather than just be able to make the predictions, we're going to try to develop a distribution of graphs. One particular example that is easy to explain and is going to be our baseline that we'll compare to constructs graphs in a node by node way. So based on all of the embeddings of the graph so far, it'll determine whether to add a new node. And if so, it'll then construct all of the edges to any of the existing nodes based on the node embeddings. Generally speaking, though, the literature in generative graph neural network models doesn't particularly focus on important statistical properties of graphs like the degree distribution or the local clustering coefficient distribution. So could we focus on those instead? In particular, sparsity is a really important property of graphs. So sparsity related to the density of the graph, where density is given as the total number of realized edges out of the total possible edges. So here I've given what that would be for an undirected graph. And that's a really important and simple property of graphs. And we have a lot of work on models for graphs that are dense or that are sparse. And we know that in a lot of real world graph settings, graphs are sparse. So if you think about a social network, most people in the network are not connected to most other people. The graph is sparse. However, a lot of the generative GNN models are going to produce dense graphs by construction. There's some work that shows that they're graphon-like, and we'll end up with either empty or dense graphs, but not really be able to construct sparse graphs. So for that, let's go take a look at some recent work on sparse graphs, and we'll see if we can tie these together. So, whereas the model I just talked about, the node-based model, we're going to look at edge-based methods that are known to be able to produce sparse graphs under certain constraints. So, as a motivating example, we're going to think about this graph model that's the binary Hollywood process, where we already have a graph with vertices Vn and edges En. We're adding a new edge with a sender S and recipient R. We're going to preferentially select the sender for this new edge based on the degree of each node minus a constant, or we'll have select a new node as the sender for this edge with probability alpha plus scaling times the number of nodes in the graph. And we have a similar construction there for recipient. So As an example of what those kinds of graphs look like, we do allow for repeated edges, we allow for self-loops, but we have this preferential attachment, so nodes that have been selected before are more likely to be selected again, with a sufficiently large probability of selecting a new node for every single edge. As long as that probability remains sufficiently large, we'll end up producing sparse graphs. While a model like this is great, it would be really lovely if we could include things like node covariates, a more flexible structure. And so that's exactly what we're going to propose with a edge-based generative graph neural network. So this construction should look somewhat similar to that previous slide, where we'll have a neural network based on node embeddings and an overall graph embedding to select the sender or to select a new sender, and so forth. As we add each edge, we'll do a round of message passing to update all the embeddings. And we also explored a version where we weight the messages by time. So in that case, we would allow for capturing temporal dynamics that are in the graph construction. So first, let's see, can our model replicate behavior of these binary Hollywood process graphs? So a graph that we know is producing sparse graphs. And we have a particular realization from the test set up here. On the left, you see the ground truth sender probabilities. So how to interpret these: if edges are added from top to bottom, nodes as they get added to the graph are added from left to right. And we're showing the probability of selecting each node. So we see that certain nodes become popular. Those are the streaks that we see where their degree is higher. We're in this preferential attachment scheme. They're more likely to be chosen again. But we also maintain a probability that's sufficiently high of selecting a new sender. That's that frontier along the right edge. On the right is our reconstruction. So we trained a model on these type of graphs. We're able to more or less replicate the same kind of behavior. In particular, we then looked at the sparsity of graphs that we generate from our model as compared to the theoretical behavior of these graphs that's shown in the black line, and compared to the test set graphs that are shown in red there. And more or less, we're able to produce graphs with the same level of sparsity. So with a given number of edges, we're producing maybe even slightly more nodes, slightly sparser graphs. That kind of makes sense by construction for our model. And then we wanted to explore other types of graphs. So here, each row is a different graph data set with ground truth graphs shown in the first column. And the graphs on the far right two columns are generated from our model that's been trained on each data set. And I love this figure because you can see that we're able to construct very different kinds of distributions on graphs using our method. The second column is our baseline that we're comparing against. But I love the ladder graph row in particular, that we're able to construct graphs that look very similar, that we're able to construct this without assuming that from the get-go. So on those same four data sets, we looked at the statistical properties of the generated graphs from our model in the first two columns versus the baseline. And we compared the MMD on the degree distribution, clustering coefficient, spectral density. We'll go into more details about those if needed. But our method is able to more closely reconstruct graphs with similar properties as those in the test set than the baseline, generally speaking. So that was a really encouraging result. We then looked at some real world data sets that all have temporal behavior. In this case, we saw that the baseline model seemed to do a little bit better. There's a couple of reasons for that. Our method is going to construct multi-graphs, so we'll include repeated edges. Those are removed when we're looking at these statistical properties. So our method may be constructing things that might look a little more similar, but based on our comparisons, the deep GMG is more likely to do that. But another reason is we know that in these real world data sets with lots of repeated edges, we're going to send more messages than the baseline model. And there's results in graph convolutional networks that having too many layers can result in node embeddings that are over smooth, where they become indistinguishable for different nodes. So we send considerably more messages. We could explore reducing the number of messages, for example, rather than sending propagating messages around the entire graph, maybe we just propagate over edges that were added within a certain time window. But still encouraged here, we're able to replicate the behavior of different kinds of graph distributions. Did well on synthetic results. Maybe we need a little bit more work for some real world graphs. And with that, let's wrap it up. These projects all explored using stochasticity and neural networks. We looked at an smarter, but perhaps not different approximation with spike and slab for PVP. We looked at applying non-parametric learning inference methods to normalizing flows in a unique and interesting way. And then we looked at this generative graph neural network model that's able to produce sparse graphs. So with that, thank you for being here. If you have any questions, I'd love to try to address them.
So I think we have, that sounds a little late. We do have a couple of minutes if you have any questions from the floor.
Yeah, so maybe I can go first since I have a 10 o'clock, 11 o'clock hot deadline. So I was wondering for the generative gen method, do you have any comment on the potential application for downstream task? For example, what type of downstream task can benefiting from this type of generative model?
Sure. I know generative neural networks are used for like potentially you could do like drug discovery type problems. That's the most salient example I know about. I suspect that anything that you could approach from a GAN type perspective, you could also use a method like this if you're working with graphs rather than other types of data. Yeah.
That sounds good. So so my understanding is at this moment you primarily measure the performance by checking some summary statistics of the generated graph and the true underlying graph. Is that true?
Yeah.
Okay. So what you mentioned is like potential thing for drug discovery. So that type of thing is not yet included, right?
Right. Yeah.
So do you think this approach has potential to extending to that domain?
Maybe. So I will hedge a little bit there. I would suspect that in that paradigm, I would imagine that some of the molecules that you would want to model for that are probably have a significant number of atoms. I would imagine they're probably sparse. I'm a little bit out of my element here, but I would suspect that for interesting examples that you might be able to benefit from having that sparse ability of modeling. And by the way, with our model, there's nothing that prevents us from learning a distribution on dense graphs, but it's just we're also able to produce sparse graphs. So I suspect that removing that constraint of only being able to produce dense graphs, I suspect that could be helpful.
I'm going to quickly interrupt and also say I know Ming has to go very quickly, but since we're sort of segueing into committee questions, I'd like to thank everyone for coming and ask those of you who aren't on the committee to please step outside or leave the call. Thank you so much for joining.
Yes, thank you. So I can go ahead and end the recording, maybe, or.
Yes, I would end the recording.
uh,